Assalamu alaikum everyone. So let's start lecture number 20. So today we will be moving towards the second part of our course, that is sequential logic or sequential circuits, right? So in this lecture we will be discussing about sequential circuits, latches, so and so forth. So why we need sequential circuits? So sometimes we need memory to store the data that is obtained by performing different operations, different logical operations at the intermediate stages, right? And in order to store that data, we need to do something else, which we have studied so far, that is the combinational logic, right? So in sequential circuits, there is another important signal, right? So that signal determines when we have to store the data, right? And that signal is called a clock, right? And clock is a periodic signal, right? So the basic element or the fundamental unit that can store a single bit, that is called the flip-flop, right? So the very basic type of the flip-flop is a latch, right? And actually the latches are made from the same building blocks or from the same logical units which we use in order to construct the combination circuits. For example, AND or NOT, right? And NAND NOR, right? So let's talk about the difference, the key differences between the combination and the sequential circuits, right? So when we talk about the combinational circuits, right, we will be having the output present, right, as long as the input is there, right? When we remove the input, there will not be any output, right? So this is the one main feature of the combinational circuit. So as long as the input is there, we will be getting the output, right? So whenever we will remove the input, there will not be any output, right? Moreover, the combinational circuits, they don't have any capabilities to store the output, right? And the combinational circuits, they are made from the basic units or building blocks of the digital logic designs, that are AND or NOT, NAND NOR, XOR, right? On the other hand, the sequential circuits, in the sequential circuits, we have the input, right? We have to look for the present state, right? And we are also concentrating on the next state, right? And the output is always the focal point, right? Even in the combination circuits, right? So the next state depends upon the present state, right, and the input. So you can say in the combinational circuits, output is a function of input, right? So here the output is a function of the present state and the input, right? So this is the difference, right? And the example, which is very simple example which we can have, is a flip-flop, right? So in order to construct or build sequential circuits, we need to implement the sequential logic, right? So in the sequential logic, right, output depends not only the current input but also the previous state, right? So as we have discussed memory, right? For sequential circuits, we need memory, right? Because we need to consider the previous state, right? So we need to store that state, right, somewhere else, right? So for that storage, we need memory. So what a memory is, right? So normally a memory should have three features, right? So it should be able to store a value, right? For example, if you want to store a bit, a 0 or 1, so the memory should be able to store the value, right? And then the second feature it must have, whenever we need to read the value, that what value is there at that location of the memory, right? So it should have the read capability. So the second feature is the read capability, right? And finally, we need to change the value. So the memory should have the modification feature, right? Whenever we want to change the value, a new value is there, so we have to store it, so there should be a modification or change feature, right? So let's talk about 1-bit bistable memory, right? So it can hold a 0 or 1, right? So we should be able to read the bit, right, that is there, either a 0 or 1, right? And if, for example, 0 is stored and we want to store the 1, so we should be able to change the value, right? So there are two choices, right? We can set the bit to 1, right, or we can reset or clear the bit to 0, right? So this is a bistable binary storage element, right? This is a simple circuit, but you can see the difference. The only difference is the feedback, right? So you can see here we have 2 inverters, right? But the output is fed back to the input, right? So this is the very basic memory element, right? So here you can see we have this block, right? And this is the input and this is the output, and again here you can see that the output is fed back, right, to the input. So this is, you can say, the primitive memory element, right? And the gates are cascaded, right? And we have used inverters over here, right? And this is the basic building block for static RAM, right? So what we have learned something new so far, right? So the logical operations which respond to combinations of inputs to produce an output, right? So as long as we have the input present there, we will be getting the output, right? So but in another case, let's assume that we have to add 2 binary numbers, right? So as we know that if we are using the adders, right, so we will be getting a sum and a carry, and carry has to propagate. So we have to store carry somewhere else, right? So this is the one example where you can think about the requirement of the sequential. So you can add the bits, corresponding bits, right? And then you can store the sum and the carry somewhere, and then you can move to the next bit, right? So this is the one requirement. And secondly, if I ask you to add 3 numbers, right? So you can do it very easily on a piece of paper, right? You will add 2 numbers, right? And write down the value of the resultant, right? On the side of the paper, and then you will add the resultant with the 3rd number and you will get your answer, right? But in circuitry you cannot do so, right? So you need to do something else, right? So a combination circuit cannot do that, right? You will add 2 numbers, right? And you have to store the resultant somewhere else, right? So there is the memory involved. Moreover, you also need to know when you will have the resultant, and you must take that resultant in order to add that resultant to the 3rd number, right? So this is the second point which indicate the requirement of a sequential circuit, right? So we need something else rather than combinational circuitry, right? So it means memory is involved there, and then another signal which we have mentioned clock is there, so we need the sequential logic or sequential circuitry, right? So this is the reason that we are going or switching from combinational to sequential logic. So this is the basic structure, right? You can see we have the input, right? And the main circuitry is based on the combinational logic, right? So this is the combinational circuit, right? And then this is the output, and here we have the next state, and this is the storage element where we will be storing the, for example, we have to add 3 numbers, so we will apply the 2 numbers, right, at the input, and the resultant will be stored here, and then we have to add that resultant to the 3rd number, but we have to decide when we will be having the resultant, and we will be adding the resultant with the 3rd number, right? So this is, and here you can see that we have the synchronous circuitry, right? One of the input is a clock, and on that clock you have to decide either you are going to multiply the 3rd number with the resultant, right, or not, right? Okay, so let's talk about some of the definitions which we have in our sequential logic, right? So here we have the input, right? So all the outside logical signals, right? And one important point over here is that we normally don't take clock as the input signal, right? This is only the signal that is used to control the operation, right? And then we have the output, obviously the logical signal outputs, then present state, right? The logic value of all the state variables of the systems, right? So there can be number of variables that are involved, so we have to take care about the present state of those different variables, right? Then next state, so given the present state, right, next logic state, the main difference over here is that we have introduced the clock over here, which we were talking about, right? So here input, combinational circuit, and then output, present state, next state, and this is the timing signal, that is the clock, right? So this is a periodic signal. You can see that we have a periodic signal over here, that is the clock, right? So it synchronizes when current state changes happens, right? So it controls the behavior of the system in a, so here we have cross-coupled inverters, right? So you can see that this is the inverter, right? And this is coupled with this inverter, right? So here again we have coupled this. So if we have 0 here, so that 0 will be 1 here, and that 1 will move here, and we will be having a 0 here, right? So this is one possibility. So another possibility is if we have a 1 here, right? So that 1 will be cross-coupled, right? Feedback, right? And then this one will be 0 because this is an inverter, so that 0 will be moved here, right? Cross-coupling, due to cross-coupling, and we will be having the 1 here, right? So you can see that we have the oscillations here, right? So it means the values will be there even we don't have any input, right? So okay, then let's talk about SR latch, right? So S mean set, R mean reset, so latch, right? So this is the diagram circuitry of the SR latch, right? So you can see that this is the output, right, of one gate, NOR gate, and it is feedback. You can see the feedback here, again feedback, right? So we have 2 inputs and 2 output. So this is Q, right, and this is Q bar, right? So it means if we have a 0 here, there should be a 1 here, right? If we have a 1 here, there should be a 0, right? So there is a feedback over here, right? So in order to have the output, we in addition to look for the input, we have to take care about the feedback, right? So that is Q and Q bar, right? So Q is feedback with this S, and Q bar is feedback with this R, right? So you can see that if we want to see the Boolean equations, so you can see that this is the Q next, right? And it is depending on R plus current Q, right? Q bar current, right? And whole bar, and then Q bar next, right? So this is for this output, so it is dependent on S plus Q current, right? So for this you can see that we have to take care about S, which is input, and the current state at Q, right? So let's try different values for S and R. So we will start from 0, 0 when both S and R are 0, right? So if we place 0, 0 in this equation, right, so you can see that we will be calculating Q next, right, and we are getting Q current, right? So here Q bar next, Q bar current. So it means there is no change. At 0, 0 there is no change. We will be having the same state, and that is the current state, right? So on 0, 0 we have no change, you can say no change, and the value will be retained there, right? And then 1, 0, S1 and R0, right? So here you can see that we are getting 0 for Q bar. For Q we are getting 1, right? So it means we have, so S for set, so we have set the latch, right? So it means the value is set in the latch, right? So and you can calculate by placing the values over here, right, straight away, right? And then when we have 0, 1, right, S0 R1, right, so it means we want to reset the latch, right? Q next is 0 regardless of Q current, right? So you can see we have Q next 0, right, and Q bar is equal to 1. So it means we have reset the latch, right? So you can see we have Q next 0 and Q bar next 1, right? So it means whenever we have a 0 here, so 1 here and 0 here, so it means we want to reset the latch, so we will be having a 0 here, and as a result of this 0 it should be, or it must be 1, because this is the complement, right? So you can see the reset are clear, right? So here you we have the function table, right? Or you can see this is the characteristic table. Here 0, 0 no change, we have seen that. 0, 1 0 Q 0 reset, and 1, 0 1 set, we have set the latch, right? And here we have the characteristic table, right? So this is the function table and this is the characteristic table. So here we have inputs, current state, and the next state. 0, 0 current, 0, 1 if we have, because as this is the memory element or storage element, right? So you can see that we have 0, 1, right? Or we can also have the other case, Q can be 1 and Q bar should be 0, right? So in that case it should not change, right? It should remain 0, 1, right? And in another case, right, when we have 1 at Q in the current state and 0 at Q bar in the current state, so you can see that there is no change. So at 0, 0 there is no change. It will retain whatever the value are stored in the current state, right? On 0, 1, right, so here you can see we can have again two cases. Q can be 0 and Q bar is 1 here, right? So here you can see that we have to reset the latch. In both cases we will be getting Q 0, right? So in case of setting the latch, we should have S1 and R0, right? So here we will again go for two cases. It can be 0, Q can be 0, or Q can be 1, right? So here you can see that we have, in both cases, we have 1 at Q because we are setting the latch, right? So here you can see that there is a little bit change in the behavior if we compare regarding the combination circuits, right? So here you can see evaluate the behavior of this SR latch whenever we have 0, 0, right? So the next value of Q could be either 0 or 1 depending on the current value of Q, right? So this is the difference, main difference, right? So same input, it is yielding, or it is showing different output, right, depending upon the previous state of the input. So this is something different from the combinational logic, right? Because in combinational logic, if we apply the same input 2 times, 3 times, or maybe more number of times, we will be getting the same output. But here we don't have the same sort of behavior, right? If we are applying 0, 0, right? So maybe one time we will be getting 0, 1, right? Or another time we will be getting 1, 0. What is the difference? Depending upon the current state, we will be getting the next state. So this is something different from the combination logic, right? So what about SR11, right? So here you can see that when we have S1, R1, right? So this is practically impossible because we cannot set and reset at the same time, right? So if we want to calculate, right, by putting the values in the equation, so you can see that we have 1 here, and regarding the Q bar we also have the 1, and that is not possible because we have already said that Q, right, and then Q bar. So it means if there is a 1 here, there should be a 0 here, and if there is 0 here, there should be a 1 here. They should be a complement, right? So Q and Q bar. So this is not possible, right? And in another case, you can see that we have 0, 0. That is also not possible because they are complement, right? So Q and Q bar, they are complement. They should be 1, 0 or 0, 1, right? So this is not possible. So we have named this situation as the race condition, right, or invalid. So this is the whole story regarding the SR latch. You can see that we have SR latch with NOR, right, and this is reset, this is set, and we have the feedback, right, and this is the function table, right, 1, 1 undefined or race condition because this is not possible and this is not valid, right? If we talk about the Boolean algebra or Boolean laws, so this is not possible because the Q and Q bar is the complement of Q. So if 0, we should have 1 here, 1 we should have 0 here, right? And then 1, 0, S1, so it means we want to set the latch, so it's 1, 0, right? 0, 1, we want to reset the latch, so 0, 1, right? And 0, 0, no change, right? So if we have the previous state 0, 1, it will retain the previous state. If we have the previous state as 1, 0, so it will retain the previous state, right? So this is the summary of SR latch, right? So these are the symbols, right? As we know that we normally use symbols in order to construct or design circuits, like we have symbols for NAND and OR, NOT, right? NOR, XOR. So similarly we have the symbols for SR latch, right? So here you can see we have S, R, Q, right? And this is Q naught or Q bar, right? We can also place a bar here, right? So here you can see SR, or sometimes you can see that there is a bubble here. So this bubble indicates the inversion, right? But this is not allowed. You cannot place the bubble and put the bar at the same time. So this N is actually the bar, right? So here we have SR latch, but we have complemented the SR, right? So you can see the bubbles at the input of the S and R, right? So this is Q and this is Q bar. So this is the, you can say, function table in addition to the characteristic table, where we have the current state and the next state, right? So you can see 1 1, right? So no change, right? 1 0, right? 0, right? And 0 1 we will be having 1, right? And we have to avoid 0 0, right? Because this is SR latch that is based on NAND gates, right? So in NOR gates we have to avoid 1 1, and while we talk about SR latch with NAND gate, we have to avoid 0 0. We will see in a couple of moments, right? So here I just want to mention the characteristic table. So you can see we have the characteristic table over here, and this is the these are the values, right? SR, right? And here you can see that we have the 0 0 and different possible values, 0 1 1 0 1 1, right? And then we have the action and the current state, the next state, right? Right? And you can see we have the different unavoidable conditions, or we can say that say them as race conditions, right? So here we don't have the control signal. Up till now we don't have introduced the control signal, right? So you can see that we have the input and the output, but we don't have introduced the control signal. So let's talk about the control signal, right? So you can see we have a steering gate over here, right? So we can control the logic, right, or the flow with the help of this control signal, right? So this is the NAND gate, right, with inverted, that inverts the input, right? So you can see that we have signal, right, over here, that is being inverted, right, whenever we have a 1 over here. And whenever we have the control 0, right, so you can see that signal is passing to the output, right? So this is when we have the control 0, right? And then we can have the 2 input circuitry, right? So here you can see that we have the control 1, right? So it means gate is open and we are getting the inverted output, right, over here. And whenever we have the control 0, so it means gate is closed, so there is no output over there, right? So output is disabled over here because we have the control 0, right? So here let me introduce SR latch with control input, right? Because before we only talked about SR latch, right, and there is no control. So here you can see that we have the SR, right? So this is complement, this is again complement, and there is another circuitry, right? So we have introduced this circuitry in order to have this control signal, right? So here you can see that we have the control 0, right? Irrespective of the values of X, S and R, no change, right? So here we have control 1, right, on 0 0, right? no change. 1, right, 0 1, right, 0. So because we want to reset, see, because R is 1, so we want to reset the latch, right. So here 1 0, we want to set the latch, set mean 1, so here we have to avoid 1 1, right, because we will be getting the race condition, and that's why we have to avoid this input, right. Okay, so you can see that we have the dotted blue box, right. So that is the same latch we discussed before, right, and this is the additional circuitry, and that has been introduced in order to have a control over this latch, right. So this control input is the same as we talk about the enable or disable, right. Okay, so that's the SR latch with NAND gate, or although you have already seen the latch with the NAND gate, so here we have the summary of SR latch with NAND gate, right. So here you have the NAND gate, and this is the output, and that is feedback, right, and this is also the feedback, right. So this is the table, right. You can say this is the function table SR, right, mentioning the functionality SR Q and Q bar 0 0, this is 1 1, right. So we have to avoid this, right, disallowed, right, and then 0 1, it means we want to reset the latch, right. So here we have 1 at Q, right, and 0 at Q bar, right. So we have set the latch, right, and then here 1 0, right, reset, so 0 1, right, 1 1, so we have no change here. It means the value will be stored, will not be changed or will not be affected, so we will be getting the previous state. If we have a 0 1, it will be retained, and if we have 1 0, it will be retained also, right. So here we have avoid 0 0, because this is the NAND, right, and for the NOR SR latch with NOR gates, right, we avoid 1 1, right. So these are the latches, right. This is the latch with NOR gate, and this is the latch with SR latch with NAND gates, right, and you can see the function tables, right. Here we have set state, reset state, right. So for NOR latch 1 1 is a race condition, right. For NAND latch, for SR latch with NAND gate 0 0 is race condition, right. Okay, so this is the same SR latch with control input, right, enable input, right? So here we have the sensitivity, level sensitivity, right. So here you can see that the sampling, right, enabled by the gates, right. So latch is enabled with this C, right, and then those inputs are being sampled by these gates, right, and then the output change when C is low, right, because this is the complement, right. So it means this is active low, right. Reset and set otherwise whole, right. So this is the level sensitive latch, right. So you can see that the input is being allowed or gated, right, whenever we have this 0, right. So input will be passed to the next state whenever C is 0, because this is active low, right. So there are some problems with this latch, SR latch, right. The first problem is that we need two inputs that are S and R in order to store a single bit only, right. So this is the first problem, right? And the second problem is that a control input is also required to place the device in a hold state, right? And finally, there is a race condition over here, right? Like in case of NOR latch, we have to avoid 1 1, right? And in case of NAND latch, we have to avoid 0 0, right? So these are the problems. So in order to overcome those different problems, we have introduced D-latch, right? So you can see that we have a SR latch over here, right? So we have the function table, right? Here we have XY, this is the control or clock, right? And Q bar, right? So what I did over here, I have inverted the second input, right? So I have marked this with D. So if D is attached with X, right, then this has to be complemented and fed as to the second input, that is Y, right? So here you can see if I pair them, so I will be having 0 0, right? So this is 1, so this is 1 input, right? And then I will be having 1, so I can only have 2 possibilities, right? Moreover, by doing so, we will be avoiding the race condition, right? 1 1 at least, or 0 0. So we have 2 race conditions, 0 0 and 1 1, right? So we cannot have 0 0, right? Or we cannot have 1 1 at the same time. So it will be a 0, right? And here we have 1, right? So you can see D, clock, then Q and Q bar. Q 0, clock or control signal 1, so we will be having 0 1, right? So 1 1 1 0, and if we have clock 0, irrespective of the value of D, we will be having the previous state, right? Retained or previous state. Okay, so here you can see that Q follows D, right, on the clock signal, right, or on the active enable signal, right? So it can be active high or active low, so Q follows D. So this is the reason for the introduction of D-latch, right? So here you can see we have the same D-latch, right? Q follows D, right, on the enable high, right? Right. So here you can see that we have the block diagram, right, or the symbol for D-latch, right? So this is the D control signal, that is enable, and this is the Q, right? So here we have the different signals, right? This is E, that is, you can say, the control signal, and this is the input, right? And this is the output, right? So it means you can see that whenever we have high, E high, right, we will be having the Q follows D, right? So this is Q and this is D, right? So Q follows D on the active enable signal, right? So you can see that we have Q follows D, so it started following over here, right, whenever we have the enable high, right? So it started following D, and whenever it is, you can see that it goes low, right, because the enable is still high, right? So enable is low, it will retain its value, right? So this is the timing diagram, you can say, of the D-latch, right? Okay, so these are the symbols, again symbols, because now we have another addition of D-latch. So this is the SR latch, this is the SR latch with inverted or complemented inputs, right? So SR latch can be made from NOR gates, right, as well as from the NAND gates, right, and D latch can be based on both NAND and NOR, right, but SR latch is based on NOR gates, right, and R complement latch is based on NAND gates, right. So that's all for today's lectures, right. So today we have discussed latches, right. So actually the latches are based on combinational circuits or combinational gates, NAND, NOR and OR not, right. We can also have the combinational circuit at the input, right, and the latches, they can store the data, right. See, so the problem over here, or the reason for moving from combinational to sequential logic, that we need the memory and we need sequential control, right. So that's why we have introduced the sequential logic, and latches are the basic building block for sequential circuitry, right. So we have discussed the SR latch, right, and in SR latch what we did over there, that we have cross coupled the gates. If we talk about the NOR gates, we have cross coupled them, right, and we have introduced two input signals, one for set and the other for reset, right. But the problem with SR latches is that we came across the race conditions, right, that violate our basic principles of digital logic design, right. So in order to overcome those different problems or race conditions, we introduced another latch, that is the D latch, right. So in D latch, Q follows D on the active edge or active enable signal, right. So we have overcome those two different problems, right. So that's all about for today's lecture, right. So अपना ख्याल रखिएगा, मेरी तरफ से अल्लाह हाफिज़, अस्सलाम वालेकुम.